In this video, we're going to discuss displacement, velocity, and acceleration, and how to use calculus concepts to solve them. This video can also be used as introduction to integration later on when we get to that lesson. So what we're provided here is several questions about this graph, which is velocity versus time graph of a toy train, which starts out moving north, and the position it starts at is 2 meters north of some sort of reference point. Part A, we're going to find out the displacement of the train in the full 25 seconds from start to finish. And displacement, as you know, is when we take the velocity, it's the derivative of the displacement. So velocity is the derivative of displacement. We're given velocity to come back to what displacement is something called antiderivative. You do not need to know antiderivatives at this time to solve this question because this graph is made out of linear pieces. So let's start off by, first of all, discussing the following. This 2 meters here and the y-intercept being 4 here. Please do not think there is a mistake because this 2 meters is talking about position or displacement, versus this graph is about velocity. Here's the main thing you will need for this. From the original graph, if we're going to look at the slope, we're going to get the first derivative. When we look at those slopes, we get the second derivative. When we're going back, instead of looking at slopes, we're going to be looking at area under the curve. So area under the curve of second derivative will give us the possible first derivative, and then area under the first derivative will give us a possible graph of the original f. Please recall what we've already mentioned, that f will be called displacement here, first derivative will be velocity for us, and the second derivative would be acceleration. So the reason why slopes and areas under are inverse operations to each other, that's something we'll be discussing later on when we get it to integration unit. For this question, because we're going to be doing areas under the graph, we have the following reminders of shapes. Area of a rectangle is length times width, area of a triangle, base times height over 2, and area of a trapezoid. If we have this trapezoid like this, we have two parallel sides of length A and B and height here, then the formula is as follows. So let's start off with this region in yellow. That looks like a trapezoid. We're going to think of this side right here as A, this side as B, and the height going horizontally. So on the interval from 0 to 5, the yellow region, we're going to use the trapezoid equation of an area, and when you fill it in, you get 27.5. Okay, you could pause to verify my calculations later on. Next region is this blue one. This blue region is from 5 to 8 seconds, and that region is a triangle, so here are the calculations for that area of a triangle. Now let's discuss units. Why does area under, even though this is not a true proof, but why is area under going to give you displacement? So let's look at height of this blue triangle. Height would be 7, and height is meters per second because it's vertical, and the units vertically is meters per second. The base is 3. 3 is along the x-axis here, which is time in seconds. So we have seconds being multiplied by meters per second, and that gives it just meters. So it does imply that this is going to be displacement. With trapezoids, same thing happens because the 5 would be the unit horizontally, and 4 and 7 both together are the vertical ones, which is meters per second, and in the same fashion we get meters out. Moving on to the next region. This region is under the x-axis, but we could still evaluate this area. So on 8 to 10, base times height over 2, because this is still a triangle, we get a -5. Let's talk about this negative. If the question asked you to find distance, total distance traveled, then you would discard that negative. But because it's talking about displacement, displacement has direction as well as magnitude. So you have to keep that direction that it's going now in the different direction. Instead of north, it's going south. Next region, we have a trapezoid. And using those calculations, you'll find this. So at any point, you can pause the video to verify my calculations. And the last one, I could have done this with a rectangle and then a triangle. I just went with one more trapezoid, and we have this negative 45. So to find out displacement of the train, we need to do the following. The 2 is where we started from, 2 meters north, so 2 is positive. On the region from 0 to 8, so 0 to 8, the velocity was positive, so the train was still going north here. And so we take the values we got from the yellow region and the blue region, and we add on top. Then the graph for velocity was below the x-axis, so the train was now going in the south direction. And so when you subtract those values to find your overall displacement, you would get this value. So it's 37.5 meters south of the reference point or the origin. For part B, what is this train's average velocity? So average velocity is just the change in displacement over time. And from the previous question, we already know that at the end, 37.5 meters south was the ending position, and we're told the starting position. So from grade 9 slope equation, we know that displacement final minus displacement initial all over the differences in time. When you substitute all the values in, you would get this negative value. Again, just to prove to you that you're getting the right units here, displacement is measured in meters and time is in seconds. So meters per second is the result for the average velocity as well. Next question is almost identical. It says, what is the average speed? So let's discuss the difference. Velocity is speed with direction. Speed is just magnitude, no direction. So technically, I should have been using a slightly different notation, which you will see in vector unit. Velocity is going to be with a V with a little arrowhead on top of it to indicate that there is direction. And speed could have been recorded just plain V without that arrowhead. Same thing with displacement. So think of displacement as change from the original position versus D, which is not a vector, could be just total distance of travel. Okay, so back to this calculation, let's adjust it if we think about it as a velocity. So we should have these arrowheads for direction on it. And the final answer, this negative right here, will be interpreted as south direction and drop the negative. All right, so on to question C. We want to find average speed, which is change in distance, notice not displacement, over time. Now, taking our answer from prior slide, we had displacement, all of these calculations from before. I'm going to tweak it a little bit. Instead of displacement, let's think of it as total distance traveled. All these negatives, turn them into positives. But remove 2, because 2, that was at time 0. We never actually traveled anything at that point in time. So you just want to add the differences of distances. Okay, and you get this value here for the distance. You put that under distance and total time interval is still 25. When you divide them, this is the average speed, which is different from average velocity. All right, question D. What is the average acceleration of the train? Average acceleration will be the derivative of velocity or rate of change of velocity, or you could think of it as slope of velocity graph. because this is just average on the whole interval, so we can look at the slope or slope of the secant of this graph on the interval from 0 to 25. And so you could do rise over run if you wanted to. So it went down 4 and over 25. So you could see these numbers and you get this value. You can again look at the units. Velocity is measured in meters per second. Time is measured in seconds. So overall, this is meters per second squared, which makes sense for this to be acceleration. Question E. Draw the position versus time graph. So I'm going to take something from A. So again, the stuff that we calculated from A, just made it bigger to have it here. And here's my setup of position versus time graph. We know it starts at 2 because we were told 2 north. So we're going to assume north is on top. So let's start with this region over here. That calculation was 27.5. So I'd like you to think 2 added with 27.5 gives us this value. So this is the new position. The train went north by 27.5. So right now it is 29.5 from the reference point. Next region, the blue one, it's going to be added to 10.5. So the train continued going north. So now we are at 40 from the reference point. So from 29 to 40, we just added this blue one. Next, velocity went in the negative. That means the train turned and went in the other direction. So it stopped and started reversing. Okay. This area was 5, but it's negative because it's going in the opposite direction. So the train now is coming closer back towards the origin. So we're now at 35 meters from the origin or reference point. This region is next. That was the value right here. Take 35, subtract 27.5 from it, you get 7.5. This is now the position of the train at time 15. And this last piece right here was this 45. So from 7.5 subtract 45, we would get this final displacement value. Next, from before, we've already discussed this. If the first derivative was increasing, that means the original graph was concave up. So we have 2 increasing pieces of the velocity. This region right here from 0 to 5, and the last piece right here, which is also increasing velocity. And so that means the original displacement graph or position graph will be concave up here and here. Next, if the velocity graph is decreasing, then the position graph will be concave down. So we have falling slopes here, right? Or falling graph. So decreasing here and decreasing here. So both of these regions will be concave down. If we have a horizontal piece, that means we're going to have a constant slope. So here is the horizontal piece right here. So it's going to be a straight line here. So I know this kind of looks like a straight line too, but it's a little bit hard to draw because of the scale that I've chosen. Okay, last question, F. Draw the acceleration versus time graph. So I've set it up with our time intervals going by 5s. And we're going to look at the interval from 0 to 5. So to find acceleration, we know that it's slope of the velocity or the derivative of the velocity. So slope here is going to be rise over run. So rise here is 3 and run is 5. So we have 0.6. Looking at units, velocity is meters per second, time is seconds. So this is meters per second squared. And because acceleration is a vector, so it has to have direction. So if you get a positive value, please record the direction beside it as well, which here is north. So that means it's accelerating in a northern direction. Then you plot this on the graph. Notice how there is an open circle at the end here. I'm going to remind you that derivatives or slopes at a sharp point do not exist. So acceleration will be undefined at this value of 5. Then you proceed to the next segment to do the same thing, and you get a negative value. So we have acceleration in the southerly direction. Remember, it does not imply that you're directly going south. It's just there is a pull in the south direction. Okay, in terms of discussion, where is it actually going and whether it's speeding up or slowing down? So in this region right here, from 5 to 8, velocity is above the x-axis. So velocity is positive. That means the direction is going north. But at the same time, we know the acceleration here is a negative value, so it's being pulled towards the south. So the train is slowing down in this region. Then from 8 to 10, the velocity is negative, so it's going south, and it's being pulled in the south direction. The acceleration is going south, we just said that. So here we'll be speeding up in the south direction. All right, so if you understood that, we'll move on to just plotting that. And similarly, the next section, you find the value, you plot it. The next region is flat, so the slope here would be 0, or acceleration is 0. And last region here, we have positive slope, so acceleration here is being pulled towards the north. Doesn't mean that the train itself is going north. Let's discuss this again. Velocity here is still in the negative region, so the train is going south. But it is being pulled in a northerly direction, so the train is slowing down, and you can even see that the value of the velocity goes towards 0, so it definitely is slowing down here. And so you just have to plot this at the end here, and this is it.